Here is the goal. The goal of this lab, this is our Atwood Machine Lab, is actually to determine the mass of this guy. How many grams or kilograms is this? And we cannot use the scale over there. Bummer. We can use the scale to find things like the mass of the string, but really we cannot go ahead and just throw this down on it. That'll be us kind of checking our work later. So we have, of course, the green cart. We have this string, which has a mass of 2.28 grams. So we know that now. And we have this motion sensor with, this isn't an L, that's a 7, with kind of all of the Logger Pro software. So we could hook this up to the computer here, and we could get graphs of velocity in time or displacement in time. And then we also have this set of masses. And last but not least, we have a pulley. The pulley's pretty simple. We can just kind of hook it right here, and then we can just kind of hang a mass off the side there, and that should work for us. So what I need you to do is design a procedure. Type in step 1, step 2, step 3, kind of write into this document, or you could write it on a piece of paper, explaining how the heck you'll find the mass of this guy. Now, a hint I will give you is maybe you choose to use, I don't know, a kilogram. So that's 500 grams plus 200 grams plus 200 grams plus 100 grams. This is a kilogram, so we can kind of break it up in different ways. My hint that I would recommend, if you want a hint, if you don't want a hint, stop the video. But the hints that I would recommend is you could put the masses on here, and if you choose to take a mass off of here, it needs to be hanging off the side. If a mass isn't hanging off the side, it's on here. And the reason I'm saying that as a hint is then the mass of the system doesn't change. It doesn't matter if this guy's hanging off there. The whole system that's moving is always the same mass. So that's my hint. So we've got everything set up. And what I've chosen to use is, well, my 1 kilogram is just like my stop. It's just my brake here. I have 100 over here off the pulley. We can kind of check it out right here. And so the moment that the pulley, actually this needs to slide a little bit so it's nice and lined up. The moment that I move the brake, well, this is gonna be pulling down on it here. And so this is my net force. That means my net force is caused by this 100 grams getting pulled down by gravity. Now the force of gravity pulling this 100 grams is not just accelerating the 100 grams though, it's accelerating everything in my system. So it's accelerating this, it's accelerating all of these masses, it's accelerating the green car as well. It's not accelerating this because I'm just gonna move it out of the way. And so what we'll do then is I will come over here, I'll hit start on our data collection, and the motion sensor will start. And so we'll get a graph of the position versus time, as well as the velocity versus time. And from that, we can actually go ahead and kind of get some data to determine it. And what we'll really want from this is, well, actually the acceleration value. And so what I can do then is I can delete this graph and make that guy bigger. So let's go for it. Okay, now the important part from this graph, well, what the heck can we get from a velocity versus time graph? It's the acceleration. So that means the slope of this will tell me the acceleration. And obviously, once I stopped the thing at the end, it's not accelerating, which is perfect. Or it's not, it has no velocity and it's not accelerating. It has zero slope and it's a long zero on the line here. Same thing before I let go. Now here I have this little funny wobble, so I want to ignore that. I don't want that screwing up my data. So I want to look at this nice, relatively straight segment before it starts kind of bending. I would call this little portion like the knee of it because it kind of bends like a knee does. I really want just this part. So I want to just click and highlight and then go analyze linear fit. Once I have a linear fit, oh, look at that. I can figure out what the heck the acceleration is. I can even check and go, well, let's go back a little more and see if that changes it. We get here that the slope is 0.5949 meters per second per second. So now we know the acceleration of not just the mass that was hanging, not just the cart, but of that whole system, okay? And so really, we immediately know A, and we can use that in Newton's second law, F net equals ma. Now, here's the idea. Just to kind of reiterate, we now have found the acceleration, and we got that the acceleration was, I think it was 0.59 something. Let's find it. 0.5949 meters per second per second. Great, awesome, terrific. And the goal is to find the mass of the cart. Now, we know that right now there's a kilogram on top of the cart because that includes these masses and the one hanging over there. And there's also the mass of the string as part of the system. If we could get the mass of everything, because we have no idea what the heck this is, if we could get the total mass, well, if we could find this guy here, well, then we could just subtract off all the other stuff that's on the cart, that's part of the system, and then we would suddenly know, well, the mass of the cart. So the idea is that we can use Newton's second law. The net force is equal to ma, where m is the total mass. And we know the acceleration. We already know the acceleration, which is pretty sweet. So what we need to do now is figure out what the heck is this net force. Because if we can find the net force and we can know the acceleration, boom, we suddenly can find the total mass, which we then can subtract all that stuff from to get the mass of the cart. So what the heck's causing the net force? Well, it's the force of gravity on my 100 grams. That's what it really is. But 100 grams is the same thing as 0.100 kilograms, because again, force has to be in newtons, and newtons is kilograms meters per second, which is a weird thing, per second. So really, we have to just do our mass. Force of gravity is just mg, so we have 0.100 kilograms times 9.8 meters per second squared. Well, timesing by 0.1 is just the same as moving this decimal over, so our net force is 0.98 newtons. So we know this. Let's just plug it in there with our known acceleration, and you now have the total mass. From that total mass, we'll subtract away a kilogram, and we'll subtract away the mass of the string, and you suddenly know the mass of the cart, which is pretty incredible, right? Now, what I want to do though is I don't want to just do this once, because maybe there's some error here. Oftentimes in an AP exam or AP type question, they want you to make sure that your errors are reduced. They want to reduce experimental uncertainty. And so what we're going to do is we're going to take this 100 gram and put it back here, and we're going to put a 200 now over here. So I have not changed the mass of the system, I have just changed one part of that system, and that really is just the net force, because now we have gravity pulling on 200 grams. So we're gonna go ahead, we're gonna do the same thing again. I wanna get rid of my curve here for it. We'll make sure that we can record our screen along with us, and you can see both in real time. Okay, and we'll go in just a moment here. 1, 2, 3. Okay, we can see here that there's some craziness in the graph. And that's because I reached in here. So this is actually my hand moving in and my hand moving out. But right here, I can see this nice, relatively smooth acceleration. That's the part that we care about, and that's the part that we're going to do the linear fit on. And here I can see that we have an acceleration of 1.178 meters per second per second. When we have more mass that's getting pulled, we have a bigger net force, so we accelerate more. And that checks out with what we would have expected. And so now we can use this new acceleration value. And from this new acceleration value, we will actually calculate the mass of the total cart again with this new net force, because now we have a new net force, we have a new acceleration, we can find the mass again. It's getting a little dicey now because I have 300 grams over there and it was starting to pull everything, including my kilogram mass. So this will be our last heavier one, and then we'll actually go down and do a lighter one. But again, there's 300 grams over there, which is 0.3 kilograms that's getting pulled down by gravity. And so I'm just gonna pull it over and we'll actually start taking our data. One, 2, 3. Okay, yeah, we can tell it got a little more exciting there. We lost some mass. That's okay as long as the cart is fine. Okay. Now we can see here that actually this had a really nice slope for it. This looked really clean, in all honesty. And so I can just select this little section. I want to kind of avoid the knee at the end. I could have gone a little earlier. We go over it. We want to do a linear fit. And there we go. We have a new acceleration to match with our new net force. And so we can find the total mass now a third time. And that should allow us to find the cart's mass a third time as well. We're on to our last trial, and what I've done is I've foregone the 100 gram that was sitting here. It's not over there. It's actually sitting right here in the box. But maybe you're going, wait, you said don't remove the masses. Well, I put this 100 back, but now I have 100 in these little tiny guys here. We have a 50, we have two 20s, and we have a 10. The 10 is just dainty. And so we'll put the 20s on here, we'll put the 10 here, and we'll just end up hanging a 50. And so we've done it with 100, we've done it with 200, we've done it with 300, we'll do it with 50, and we would expect that since the total mass is still the same, but now there's way less hanging, we'll have a smaller net force, well, we should have a much smaller acceleration. And with both of these known, we can still find the total mass, we can still subtract off our 1 kilogram plus the mass of the string from that total mass that we'll find, and we should still get the same exact mass of the cart. And then we'll throw it on the scale and we'll actually see what our cart really should have for a mass. And let's start. This will be nice and easy now. Ooh, smooth like Sunday morning. Now, we can see here on the graph that it is a heck of a lot smaller. So I want to go and I want to change. I want to see if it'll maybe just auto scale and do the smart thing for me here. Whoa, that looks crazy. We can see these little imperfections in it. If we looked at it before, it looked flat, right? But if we actually want to just auto scale it, and that was actually a really surprising auto scale, it's kind of wobbly. There's all these little jagged bits, and part of that is the table is not perfect. There's little bits of stuff along the table that makes it wobble a little. But really, I might want to just take this section then, and we'll go, okay, well, what is the acceleration now? So we'll analyze it, we'll do a linear fit, and there we go. Our slope is 0.2610 meters per second per second. We have the acceleration now. You can find the net force now, knowing that it was 50 grams. Now that we've gone through, we've taken all of the data. I just want to point out that there actually could have been two ways to do some of this data analysis. You could have gone through and done calculations over and over and over and over. That's totally fine. That would have worked. And that's possibly how I would have done it first. The second thing you could have done is you absolutely could have made a graph. And the graph would have been something like this. And we have our y and our x. And you could have put the net force as the y-axis. And then that means our x-axis would have been the acceleration. And since this guy kind of looks like a y equals mx here, well, that means that the slope of this graph would have been the total mass of the cart. And so sure, we had 50 grams hanging, it was a tiny net force, but you had a tiny acceleration. And then later when it was like 300 grams hanging, you had a huge acceleration. And then there are a couple points along the way. Well, the slope of that would have also given us the total mass of the cart. And we would have just subtracted the masses we were using here, subtracted the mass of the string, and then we would have found the mass of the cart. And again, in case you missed it, our string has a mass of 2.28 grams, but that does have to get converted into kilograms. So now, for the moment of truth, let's find the mass of our cart itself. 499.18 grams, or in other words, that would be 0.49919 kilograms. How's that for sig figs? So now with that, one of the analysis questions is asking you to find your absolute error and your relative error, and you'll need to go back and look at our notes on accuracy and precision. But otherwise, we're done with our lab. Finish that up. Let me know if you have any questions. Thank you.